Okay. So we found that we could recover a potential function given a conservative vector field, but it has to be conservative. Folks, if you get a vector field that's not conservative, please don't go off and find a potential function for it, okay? Because it's meaningless. It doesn't have a potential function even corresponding to if it's a non-conservative vector field. Okay, so why do you care about gradient fields, conservative vector fields? Because in the physical world, they're useful because there is a physical meaning to it. So if a potential function represents some temperature, say in some conducting material, then the gradient field, that's a vector field, evaluated a point, gives you the direction the temperature increases most rapidly at that point. And we talked about this when we went over gradients like 2 months ago. Okay, so basic physical law, you're talking about heat and heat diffusion, it goes in the direction of the opposite of the gradient because things tend to cool off, not get hotter in the real world. You know, like when I set my steaming cup of coffee down on a kitchen table, it doesn't get hotter, it cools off. So it's going down the gradient. The temperature decreases most rapidly at that point in the direction of the opposite of the gradient. So heat flows down the gradient from hot regions to cooler regions. And similarly, water on a smooth surface tends to flow down the elevation gradient, down the hill. Water does not flow uphill. Okay, so here's a little example I pulled out of my math lab for you, just for kicks and giggles. So it looks like I don't have something here. Never mind. Sometimes when I do a copy, it does things do not copy. Interesting. Note to self. Okay. So we're going to do this last problem that I just took. Yeah, we skipped a page, and I don't know why that is. Let's see something here.
Starts with the question and answer. Why does theorem test for conservative vector fields work?
Yeah,
that one.
I get that, but I may not have that page. I'm sorry. Apologize. Oh, here we go. Yeah, we did skip a page. Sorry, it's back here. I had too many appended pages in my, wow, that was a mess. Okay, sorry. Why does the theorem test for conservative vector fields even work? Like, you know that the mdy equals the ndx? Like, how come that works? Like, why? Well, it's because, and you know why. If I made you think about it, you could probably come up with this little mini proof on your own. But here's a little mini proof. Hey, if you've got a vector field and it's conservative, that means it's somebody's gradient by definition. So these components here, m and n, really are representing fx and fy. They're already partials. So in other words, fx is your m and fy is your n. Okay, fine. Well, what happens when you take a partial derivative of a partial derivative? Don't you get the second partials? Yeah, you do. So when they asked you to get dm dy, I claim they were telling you to take fx and take his derivative with respect to y. Okay, so another notation that you'll see this, and you'll see this notation in a differential equations book also, is big M subscript y. So that just means take the partial of m with respect to y. And also, when you're getting fyx, well, you're taking n's derivative with respect to x. Okay. And then what do we know about these mixed partials?
Second partials are equal.
Yeah, the mixed partials, the equivalence of mixed partials, we can conclude that my is equal to nx, which you can also rewrite if you're using more of the differential notation, dm dy equals dndx. Same thing. So that's why the test works. Pretty cool, huh? It's a quality of mixed partials.
Yes, super cool.
Like, this should be like, wow, this is awesome.
Cool beans, awesome sauce,
Cool
radical.
Awesome
Talking
sauce.
to engineers rather than math majors.
Hang
Okay.
10, totally
Hang
radical.
10. Good Lord. Cheese. Yeah. Okay. Sorry. All right. So get excited, people. Okay. So now let's do the official definition of gradient fields, potential functions, and equipotential curves. So, and you'll see this in your MyMathLab homework. So I want you to get this definition. So you've got a scalar function that's differentiable on either a two-dimensional or three-dimensional region. It depends on what you're dealing with. If you've got a vector field that's exactly the same as the gradient of the scalar field, he's conservative. Woohoo! And what does that mean? That the level curves of the potential function, and you should all know how to do level curves of potential functions because that was what, section 15.1. Those are called equipotential curves. So they have a special name. So it's the curves on which the potential function is constant. You already know this. We already did this back in 2 chapters ago. Really? Yeah. And so it's all going to come together now. All that stuff that you've been learning in the past, this is where it all, you know, mix it all together with your awesome sauce and your cheese and your cool beans, you get a nice meal. Okay, so take a look at this example and then we'll go to example 4. Sorry, so we'll do this example first, then we'll skip over. So here's your scalar function. That's not a vector field. Okay, that's a scalar function. We're going to plot the gradient field with a contour map of f, and in other words, we're going to sketch some equipotential curves. Okay, so so what we're going to do, let's do the chapter 15.1 step first. So how do you get level curves? And I know some of you still have problems with this. How do I know? Because, you know, I was grading midterm 2. It was like, oh boy. You set your scalar function equal to a constant and then kind of look and see what does that equation kind of remind you of. If you did rearrange it, say. And I claim if I kind of rearrange it, I don't know, you know, like this, it looks like it's going to be what? Circles, ellipses, what?
Parabolas.
Parabolas, right. So that means you're going to have level curves that are parabolas. So if I let c equal 0, it's just going to, I can graph y equals x squared. If I let c equals 1, that's going to be x squared minus 1. If I let c be minus 1, you're going to get a whole collection of parabolas. There's your level curves, fine. Okay, now what? Well, go graph the gradient field. Oh, well, the gradient, which is del f, and you already know about gradients because we did that 2 chapters ago. Come on, people. This is old news. This is a good review for the final, though, isn't it? I love this. So you're going to go, okay, 2x, you know, the original function here, fxy here. So then the partial with respect to y is -1. Okay? So now how would you graph that vector field? And remember, we talked about graphing vector fields, you know, back in the last lecture. That was Monday. So what I'm going to do is I'm going to pick some points maybe on one of these level curves, and then I'll look at the corresponding vector that's associated with it. So, you know, I'll do like 0, 0. How about 1, 1? How about, I don't know, what the heck, 2, 4? How about -1, +1? You know, I'm picking points actually on one of these parabolas. This one right here, the easy one, where c is equal to 0. So if you look at the corresponding vector, 2 times the x coordinate, that's 0, and then just -1. Here, this is going to be 2, -1. The vector that associates with the point 2, 4 is 4, -1. Let's see, -1, 1 has a vector -2, -1, and then the point -2, 4 has the vector -4, -1. Okay, fine. So, you know, you'd go in here and you'd start graphing. You have to be careful because you have to maintain the integrity. Like this vector, if you did graph it in standard position, it's pointing down and it's only got a magnitude of 1. So it's like that. And it corresponds with 0, 0. Now the 0.11, if you graph 2, -1, so it'd be like right here, and then graph it, that is associated with a 0.11. So here's the 0.11 on the parabola, and you want to graph that guy like that. He's a little larger than the previous guy. And then the 0.24, which on the parabola looks like it's going to be up here, here's the 0.24, his vector is 4, -1. So he's like way out here. Whatever. Okay. And then this vector, -2, -1, let's see, -2, -1, that looks like it's going to be like that. And that associates with the point negative 1, 1. And then finally, negative 2, negative 4, negative 4, negative 1, which is way out here. Can you see that all the vectors are indeed orthogonal to the level curves, people?
Wow.
Say yes.
Wow. Yes.
That's the wow. So here's what I want you to note. The gradient field, that's the vector field. Okay, same. The gradient field is, and you can do some more. You can pick another parabola. I'm just too lazy to do it right now. And all those vectors would also be orthogonal to the level curves of the potential function. And so that's kind of a cool fact, cool beans for you to know, especially for some of your homework. I'm just telling you, go do it. So, and then we went to why they're so important. Okay, so I kind of skipped ahead, and then let's do this last example here and wrap it up. So here's another MyMathLab problem. And also we're going to look at some of Briggs notation, because remember I told you that Briggs doesn't use your standard traditional notation, unfortunately. Somebody asked me, I think it was Chris G, you asked me, oh, what's a good calculus book? Not Briggs. I got a whole bunch over here. My personal favorite is Larson, but Stewart is pretty good. I think they use Stewart at UCSD, and Anton kind of sucks. Another one that's pretty good, that's really hard, is John Rogalski. You know, that's a good one, but it's kind of technical, which is why we don't use it. It's kind of hard. Briggs is kind of somewhat watered down, so that's kind of why we use it, because it's not too hard to understand. But when it comes to multivariable calculus, it sucks. On a different note, did anybody hear, I heard a rumor that, tell me if this is true or not, that City College is going to shut down forever. Is that true?
Whoa.
That's excessive.
I don't know. Like I said, it's just a rumor. I don't know. Somebody told me that. And I went, what? And I guess they're going to just keep everything online forever. And I went, wow. I don't know. I know somebody who teaches there. I may want to have to ask them if that's a vicious rumor, or is that true? Okay, so let's take a look at some of Briggs notation. A lot of times when Briggs gives you the scalar function, the potential function, they use a phi, a Greek letter, instead of just a regular f. I prefer just a nice scalar function with the f, but I don't want you to freak out if you see a different letter there for the scalar function. Oh, I can't do, wait a minute, isn't phi something we saw from spherical coordinates? It was the angle that the point makes with the positive z-axis. Yes, it is. And they're reusing the Greek letter phi again for, look, I don't know. I didn't write go talk to Briggs, the guy who wrote the book. Okay. So how about arctan y over x? Fine. So we're going to plot the gradient field together with a contour map. Contour map just means go get those level curves. Okay. So, so what of it? And it turns out if you go get the level curves, that means you're setting your scalar function equal to a constant. And it's like, oh man, so you're going arctan y over x equal to a constant. Oh man, really? Yeah. Then what? and then, well, then all hell breaks loose. I would probably take tangent of both sides of the equation, and then I would get y over x is equal to arctan of some constant, and then oh yeah, but this is just some number, and then when you solve this for y, just so you could see, you're going to get some number, it's a constant, okay, times x. But aren't these lines, aren't those diagonal lines? Yeah. So it turns out the level curves are diagonal lines. I hope you can see here that somebody already drew a whole bunch of diagonal lines there. Fine. Those are the level curves for the scalar function. Now what? Well, what's the gradient? Because that's your vector field. So you're going to go, all right, I got to go get these partials. Oh, man. Do you guys remember how to take the derivative of an inverse tangent? Let's do some Calc 2 review, shall we?
Oh man, now's my time.
Yeah.
What is it? 1 over, oh, well, I already messed up.
Using the chain rule, it's that. So that's going to come into play here. All right, shall we? What is the partial of f with respect to x? You're taking the getting the gradient of this scalar function. So the u, if you will, is y over x. So u prime, what is the derivative of y over x with respect to x? Oh man. Well, the y is just a constant multiple, and I think it's going to be -1 times x to the -2, and then you're going to go 1 plus y over x squared. Okay, we'll clean that up in a minute. Ugh. And then if you get the partial with respect to y, oh man, that's going to be x times what? Or excuse me, 1 over x. I think it's just going to be 1 over x, yeah, with respect to y. And then 1 plus y over x squared. So there's your gradient, but let's clean it up because that looks pretty disgusting. Yuck. So this thing here is really -1 over x squared. And so if I rewrite the numerator and multiply that together and then bring my x squared downstairs and then distribute it, it'll make that term look a little nicer. I'm just trying to do some cleanup here. I already got the right answer. Okay, this is called algebra, sorry. Let me scroll. So when I do that and then reduce the first term for my gradient field, this looks like -y divided by x squared plus y squared. Now here, if I do a similar thing, it's like, oh, I'll bring the x down. The only problem is it doesn't make it look that pretty because when you distribute your x, gosh darn it, you still have a complex fraction. And it's like, oh, that looks gross. So what you can do to make it look a little prettier is multiply by x over x. That's the same as multiplying by 1. And then multiply these two fractions together, and then you get a gradient that doesn't look so rotten. In fact, the denominators are the same. And this is a conservative vector field because it is a gradient. Conservative vector fields are basically gradients. And so then what? Well, if you were going to graph these guys, and I'd have to make a table and everything, they already graphed some of the vectors. You'll see that these vectors from this gradient field looks kind of like a rotating wheel. It's got that look to it, whoosh, whooshing around. Those vectors are in fact orthogonal to the level curves, where the level curves are lines in this particular case. Okay, so you'll do something like that on MyMathLab, so you know, don't wig out when it happens. Now you know how to do it, okay? Would it be arctan C or tan C? Let's see. I think it would be, oh, it should be tan. My bad. You're supposed to take tangent of both sides. Sorry, guys, you're right. I'm wrong. Going back here, I did it too quick. This should be tangent of C, not arctan. And yeah, but that's still some number, right? Tangent of whatever, 5 or whatever. Okay, so that should be constant and not arctan. Okay, any other questions?
No questions.
Are you sure? Because we're going to move out of vector fields now, and I'm going to start line curves, and we're going to be. I want to finish a huge part of line integrals. It's going to be pretty gross.
Let's do it.
Okay.
Yep.
And then I'm going to hopefully wrap up line integrals on Friday. We'll see how far we get. Okay. Did I mention that the midterm is on Monday?
Yes.
Just curious.
Yes.
You haven't
Okay.
mentioned Briggs sucks yet for that.
Oh,
full
right.
thing.
No, I already did. Briggs sucks. Okay. I want to just, before I show you the next meme, remember that the word conservative has nothing to do with politics. It has to do with conservation. Conservation. We're conserving energy. And in the physical world, there's a conservation of energy. Kinetic energy plus potential energy is constant. Now, for those of you who are not clear about what potential energy is, let me just give you a little hand up because you may have not taken a physics course yet. And it is important for you to get. I bet you can understand kinetic energy, though, you know, energy from motion, you know. Hey, I'm feeling some energy and you're moving all around. Woo! I had too much coffee this morning, sorry. But what about potential energy? Well, it's where you sit. So here's a good way to think about potential energy. Let's say you had a bookcase like mine here. I got tons of books here. The books that are on the top shelf, like there, have more potential energy than the ones that are on the bottom shelf. Well, why? Because if one fell over, or if there's an earthquake, the books on the top would hurt me a lot more than the books on the bottom would, because they have a longer way to fall. So that's known as potential energy. That's a very simplistic look at potential energy. There's many more examples, and talk to your physics folks about more, but you can kind of get that feeling of they have the potential energy sitting up tall on the highest shelf, and the ones in the middle shelf have a little lesser potential energy, and so on. So I hope that helps you kind of understand the idea of potential energy. Okay, now on to this cartoon that you should understand now that you have the idea. Oops, I can't see the scroll. So this kid, he's in a high school physics class. Mr. Fox, is there a reason why you're standing on your chair? It's to boost my energy. I was feeling a little sluggish. By my calculations, standing up here gives me an extra 300 joules of potential energy from gravity, because gravity is a vector field. The teacher, but you had to expend energy to get up there. Your total energy hasn't increased. I had Steve lift me up. And then the teacher's thinking, little thought balloon, fall break, can't come soon enough. And
Well
then
said.
and then the student's like, hey, thanks for teaching us this stuff, by the way. And he's totally clueless. Yeah. Okay. And then I found this meme. It's hard to find vector calculus memes. Okay. Can easily do vector calculus. Cannot balance own checkbook. Okay. So there you go. That is another wonderful meme. You guys probably don't even balance your checkbook. Who has a checkbook these days?
Come
Right?
again.
Not for decades.
You don't even know what that is, do you? I am so old school. It's sad. I have checkbooks, and I balance mine by hand every month. My husband thinks I'm really stupid for balancing them by hand because he claims the bank never makes mistakes. So why bother? Just kind of look online and see how much
Bank
money you
never
have in
makes
your account.
mistakes.
Yeah, they're always good. So you don't need to do it by hand, because I do it by hand every month. I sit down with my calculator and all the paperwork, and I do it by hand. And it's a pain in the butt. And I'm usually the one who's wrong, because I don't know how to subtract or add. Like I'm usually off by, like $1.57 or something. Then I got to do the whole thing over again and figure out what I did wrong. And it's usually my error. I usually subtract wrong or do something really ridiculous. But last year, I wrote a check to my doctor for a $10 copay. And a month later, when I was balancing my checkbook, guess how much money they took out of my account? Let's just say it was more than $10. Just guess. Go.
Something criminal.
$200.
No,
$65,822.67.
you're closer.
Whoa.
All right.
They took $10,000 out of my account.
Huh.
For a $10 copay, and did
Nice.
not if I didn't do it, I would probably not. My husband, you would have noticed. I went, no. I don't look at my accounts too much. I just put money in there and go to Amazon and spend money. That's what I do. But I noticed it, 10,000, and that's not even like a decimal. I mean, if you think of $10, and even if you move the decimal point like 2 spots over, the most screw up you could imagine is maybe $1,000. Okay, I can kind of see that. Maybe somebody was in a hurry at the bank and they were tired. Okay, but 10,000, come on. And they didn't even apologize. When I phoned them up, you know what they said to me? Oh, well, I think you could have been the one making the mistake. You probably wrote the check for 10,000.
This is how arson is started.
And I went, I don't think so. You guys have it all on computer. You go look it up and you tell me, because they always take photos of your checks. And then they came back and they said, yeah, their finger fell asleep typing too many zeros. 0, 0, 0, 0.
People wonder why, and the banks wonder why people don't like them.
Well, that's no reason to burn them down, though. Okay. All right. So,
No, that's me.
Sounds like a Wells Fargo move.
I don't know if you heard that they did catch those 2 arsonists in La Mesa the other day, because the ones who burned down my bank on La Mesa Boulevard, Chase Bank, They caught them. That was a few months back. Okay. So I don't know why this isn't saving this. Okay, we're going to look at something called line integrals. All right. And if you took physics already, you did line integrals. Although what's really weird is if you crack open a physics book, nowhere do they say that you did a line integral because they're not mathematicians. They just do an integral. It's a regular integral, but it's not because it's different. Now you can turn it into a regular integral, but you have some work to do. So that's kind of the key. So we're going to look at these. Well, Nick G, I got to say that's scary. So we're going to look at parameterizing, and you have to be good at parameterizing a curve. So we're going to do a little bit of review of that, and then we're going to hit it and hit it hard. There's going to be 3 kinds of line integrals that I want you to know how to do. And there's going to be one of each on midterm 4, and there's going to be one of each on the final. So if you can't do these, you're going to be hurting. So I call the first one the scalar line integral. You'll hear me call it type 1. No book calls it that. I just call it type 1 because we're going to cover it first, okay? And then the second type, where we involve vector fields, I'm going to call it type 2, but it's not, there's nowhere does it call. And then there's a type 3 here, okay? So this is just Rasky talking just because I'm going to cover it in that order. Type 1 has no vector fields involved. So we're going to look at the first kind of line integral, which doesn't involve any vector fields at all whatsoever. What can you use it for? We'll get to that. The other 2 line integrals really are the same, but one of them is just a rewrite of the other one. So when we learn the type 2, it's going to turn out that type 3 really is a type 2, but they did a little bit of a rewrite of it. They kind of did some extra notation, okay? So they basically did the dot product for you. We're going to get into dot products. Well, yeah, you better know what that is. So these involve vector fields, and more specifically, you're going to use these other types of line integrals to find work done on an object as it moves through a vector field. And that's what our physics brethren use line integrals for primarily, okay? To find work done. So let's do a quick summary of what you know already, and then we'll go to what you don't know. Okay, quickie review. Are you ready? When you took Calc 1, they taught you how to look at a single integral. And you went, oh, hey, kids, you know, how do you integrate f of x dx, you know, where the limits on the integral are a and b. Okay, what are you integrating over when you do one of these single integrals?
An interval?
Yes, an interval. Very good, Ella. Yeah, you're integrating over an interval, you know, because you're going to do a to b, and there's your interval of integration. And then they use these definite integrals to find area, right? So you're integrating over an interval. How about when you do a double integral? What are you integrating over?
The region.
A region, but it's a 2D region, right? It's an area. That's why you see this area element over there. So it's an area. Okay, what about when you're doing a triple integral? You're integrating over a region, but what kind of region?
Surface.
You're close. It's a solid. Okay, so it's in 3D. So you're going to have to worry about a volume, and that's why they have the dV there for your volume element. Depends on which coordinate system you're in to figure out what that volume element is going to turn into. Okay, so now we're going to learn a brand new kind of integral. Here it is, folks. Exciting. You know all these different kind of integrals, and we're going to make you learn another one. Oh, man, I'm sick of learning new stuff. So this professor I was telling you about, who was doing surveys and finding out students are pretty unhappy right now, he said that one of the questions he asked his students in the survey was, well, if I gave you the final like tomorrow, would that make you really happy? Would you be ready for it? And would you be good with that? And you know what the answer was? Guess.
I bet they said yes.
Yeah, they said yes, but we just want to be done with this whole semester. And I just died laughing because he had to tell them, well, guys, I got some bad news. We got 5 more weeks. We're not taking
So
final.
people would rather fail the final than learn more stuff.
Yeah. Yeah, I think a lot of people are pretty unhappy, you know, trying to meet the challenges of distractions and family and the pandemic and trying to learn and study all at the same time. And some of you in the room know what I'm talking about, right? Because you've got some pretty chaotic lives going back there behind the scenes, or sometimes in the scenes when I have to mute you, and it can get crazy. So you'd like to take the final with 4 weeks left? Now, how would you like the final to have that new material on it, though? So we'll take the final tomorrow, but you haven't learned some of it yet. Is that okay? Oh, no, that would be bad. Okay, we're not doing that, okay?
Is it a good idea to eat a whole bowl of spaghetti before you run a marathon? No.
No, you don't want to be in a food coma before you run a marathon. That would be bad.
It's the
Spaghetti
same
just
equivalent.
like is spaghetti just like uniquely situated to make you like really bad at running or what?
No, you should
Carbs.
you should carb up before a marathon, but it's usually 2 weeks before, and everyone does it wrong. And the running joke is that people will just eat massive amounts of carbs before a marathon, a day before, and then habitually puke themselves the whole way.
2
Ew.
weeks, Nick, really?
That sounds disgusting. So in other words, they're running and vomiting at the same time?
Well, yeah, because they have all this food in their stomach. You're not supposed to. Well, a human isn't supposed to run a marathon to begin
Right.
with.
Right. When your belly is full of good foods, not a good plan, huh?
That's how I see taking a mid or the final right now. And if we were to do that in Calc 3, that would be suicide.
Yeah, it would be suicide, people. You got a lot more new stuff to learn. I saw somebody in the chat box, learning new things prevents dementia. Not you guys are a little young to be worried about dementia, but it happens. Okay. Let's talk about line integrals. Okay, line integrals, whoever named them should be publicly flogged, because they should have named it curve intervals, because you're integrating over a curve, okay? And now the curve could be a straight line, but more often than not, it isn't a straight line. But whoever decided the name, they just said, hey, let's just name this line intervals. Okay, fine. So we got to go with what they named it, all right? But really, you're not. So line integrals, what you're going to be doing, you're integrating over piecewise smooth curves. And this is important, piecewise smooth. And you are going to be responsible. I'm reading this to you for a reason, because I know you're not going to read it. You're responsible for parameterizing, unless you get lucky and they parameterize it for you. In other words, they gave you the vector valued function. Here you go. And some of the problems are going to be that easy. They're going to be like, hey, here you go. But a lot of times you have to parameterize it. So you have to be good at parameterizing, okay? So what does it mean for a curve to be smooth? It means that the tangent vector isn't equal to the zero vector. It means you don't have any sharp corners or cusps or crazy stuff like that. That's how you know you're smooth. And let's look at a piecewise smooth curve. I want you to notice here that you've got the first leg of the journey. They're calling that C1. And then the next piece of this piecewise smooth curve is going to travel along the XY plane. There's C2. And it's going in that direction. And then the last leg of the journey, they're going to strap on a rocket pack, a jet pack, and they're going to blast off and go straight up, although they're going to stop right there at the point 1, 2, 1. So I'm going to parameterize all 3 legs of this journey with 3 different vector valued functions. Now, when you're parameterizing, I need you to not only give me the vector valued function, but the range of time. If you fail to do both, I'm going to take off a lot of points. So follow my lead. So we'll start off easy. We're going to do the C1. So C1, and I wanted blue. And you'll notice that here's what I want. I want an R1 of t, and because we're in 3D, I want all 3 components delimited by commas. And then I want the range for what time is doing on that interval. So this is where you have to know vector valued functions. Oh, I thought we were done with all that crap. Bad news, it's back. Okay, you got to know about vector valued functions. It's a good review. Remember I told you chapter 17, you have to know everything that we did in the last, 3 months?
Yeah.
You got to know it all. Otherwise, you won't be able to do chapter 17. Okay, so what I'm going to notice is I'm starting here at 0, 0, 0, and I'm traveling along the y-axis, and then my ending point is 0, 2, 0. So because I'm on the y-axis there, the x and z components for my vector valued function are clearly zeroed out. Cool. So what is changing? What is varying? Well, the y coordinate's varying. So how about if we just let y be the parameter, t, and that'll work. And then we just have to decide now what are the starting and stopping points for time. What's going to make this vector valued function line segment work where we start at the point 0, 0, 0, but end at 0, 2, 0. Somebody tell me what my range of time will be.
0 to
Set
2.
T equals 0, 2.
Exactly. So you're just going to go, well, I'm just going to have time go from 0 to 2 seconds, and boom, you're done. So I just got done parameterizing the first leg of my journey. Congratulations if you understood that. It's not that hard. Okay, let's do the second leg of the journey, the red. Okay, a little bit different here. What do I need? I need a vector valued function. So fill in the blanks here, something, comma, something, comma, something. And then I have to figure out what are my limits or my range here for time for this vector value function. It has to match the curve exactly. Don't just give me some crap and go, oh, it's good enough for government work. If it doesn't exactly match the curve in question, I'm not going to buy it. So I'm noticing here that if I start at 0, 2, 0 and I end at 1, 2, 0, it looks like the y and z coordinates never change while I'm on that straight line. Y is a constant, it's constantly a 2. Z is a constant, he's constantly a 0. The only guy who's changing or varying is the x. So guess what I'm going to let x be here?
T.
T. And then what does t do on this interval? So it matches the curve C2 perfectly. Starts and stops. Yeah, it's going to go from 0 to 1. So you're going to put 0 to 1. And I'm done parameterizing that second curve. Okay, now let's do the vertical curve there, blasting off of Earth. I got to call it C3. So his vector valued function is going to be some vector, something, comma, something, comma, something, angular brackets. And then I got to figure out what the range is for time for that last line segment. So I'm noticing here, I'm starting at the point 1, 2, 0. I'm going straight up to the point 1, 2, 1. So 1 and 2 respectively are my x and y components, and z is varying. So how about if I let him be t? And then what is t doing?
0 to 1. 0 to 1.
Mm-hmm. Okay. Now, folks, this is the way I would parameterize this total curve, where the overall curve C is C1 plus C2 plus C3. That's legit. But when you parameterize, parameterizations are not unique. And you guys know this from coming up with the parametric equations for a straight line that we did 2 months ago. You know that your parametric equations might be different from mine, but yours might be just as valid as long as you use a direction vector that's parallel to the line, and you pick a point that actually lives on the line. And we might have different answers, but they still describe the same unique line. Now that's the same with other parameterizations, whether it's curves or whatever. Your answer may be different, but it better match the curve. Like if you're parameterizing something that really is in fact maybe curvy, like a parabola, but your parameterization is for a straight line, I'm not going to give you any points. Okay, your parameterization has to match your curve. Now for this one, I'm just going to tell you, I got this example from a Larson calculus book, and Larson is somewhere over here. Where's Larson? Up here. And when Larson did this example, if you crack open the book and read it, Larson parameterized this example totally different. And here's why. I prefer, because I'm the boss when I parameterize, as long as my parameterization matches the curve, I'm good. Do you notice I reset my clock back to 0 for each and every one of these pieces of this piecewise smooth curve?
Yes.
I'm allowed to do that. I like going reset the clock back to 0, reset, reset, every time. That's just how I roll. Now, Larson, the way Larson does it is like, oh no, you're not allowed to reset the clock. That's, come on. So this is an alternative answer. I want you to get that. It's still just as legit though, okay? So don't go, well, that's wrong. Or that one's, whatever. I prefer to reset my clock back to 0 if I can. So this is the way Larson did it. There are one, which is totally legit. There are one had components 0 to T 0, okay? But then what was their time? Well, to match the curve, since they used a 2T there, their time went from 0 seconds to 1 seconds. And you can even check it. It does, in fact, go from 0, 0, 0 to 0, 2, 0, where time goes between 0 and 1. It works. Then their C2, their vector valued function, was a little different than mine, and I'm going to go over that in a second, but I want you to see why. Because they didn't allow a reset of the clock. They wanted their clock to begin right where the other guy left off. Well, the guy before him stopped at 1 second, so let's pick up at 1 second and keep moving. Time's got to keep moving forward. Okie dokie. All right, so then how do you parameterize? Because your C2 still has to begin at the point 0, 2, 0 and then finish at 1, 2, 0. So this is how they did it. They still said that, okay, Y and Z are still constant at 2 and 0. But T minus 1 is their first component where T begins at 1. And you can see if you plug in 1 second here, 1 minus 1 is 0. And that's good because the starting point for the curve 2 does start where X is zeroed out. And then what do you think I finish my time at? If I need X to be finishing at 1. Yeah, 2 seconds. Very good. So this curve has time going from 1 to 2 seconds, and that works. And then the final parameterization, that's where we're, blasting off into space here. The R3, he, like me, acknowledges that the X and Y components are constant both the whole time, 1 and 2. But then he says T minus 2 is his Z component because he wants you to start your time at where you left off before. And then here, if you finish at 3 seconds, it'll match the curve exactly and finish at the ending point, which has coordinates 1, 2, 1. And we're done. So this alternate parameterization for this piecewise smooth curve is just as legit. It's just that they didn't reset their clock back to 0 every time. Okay? So it's up to you how you want to roll. Now, I do want to say that depending on your professor, sometimes you have to make your professor happy, as you guys know. When you take a college course, half the battle is learning material. The other half is figuring out what makes that professor happy. There are some professors who do teach Calc 3 here at this campus who I found out just through the grapevine. I don't know for sure, but they say, oh, yeah, we're never allowed to reset our, time back to 0. They like it to keep going, and that's fine. But you gotta go with whoever it is you're with. I'm gonna let you reset it back to 0 just because I'm okay with it. Okay, it's still gonna work. Your line integrals are still gonna get the same values. Okay, that's the good news. Now let's do a quick derivation of a type 1 line integral. So the type 1, the only application that I know of that's kind of legit that matches real life is finding the mass of a little wire. That's it. Now, other people may explain it in other ways. Like the way Briggs explains it is he has a whole bunch of curtains hanging down here. The curtains have some sort of mass. I don't get it, man. I've never even seen anything like that. Did I mention Briggs sucks? God. Anyway, I like to introduce it the way like Larson does, where it makes more sense. Instead of curtains, they're going along some weird curve. You got a wire, and here's your wire here. It starts over here at P0 and ends over here at Pn. And it's got some sort of density to it, and you want to find the mass of it. So what are you going to do? Because, how would you find the mass of a straight wire? That would be easy. You would just multiply the density times the length of the wire. But here it's kind of hard because the length, it's all curvy and everything. Oof. So you cut it up and chop it up into little line segments. You know the deal. We always partition into n little arcs. And then if you look at each of the length of the little subarcs, say delta S sub I is a little length. And if the length of each subarc is really small, you can approximate your total mass. So what are we saying? The mass is going to be approximately the sum of all those little subarcs of wires, where your density function is going to be some f(x) sub I, y sub I, z sub I times the little length. Okay? And of course, if you let the norm of your partition be the length of the longest subarc, and you let that norm approach 0, you know, take the limit of this Riemann sum. That's a Riemann sum, people. You're going to get an integral. Okay, so watch closely. So here's your official definition of a line integral. I'm going to give you the 2D version and the 3D version, and you have to know both for all your homeworks and exams and everything. This stuff is not going to be on midterm 3. It's going to be on midterm 4. So you have your sigma I going from 1 to n. If you're in 2D, then your density function is only a function of x and y. So f(x) sub I, y sub I, little delta s sub I is your little length. As you take the limit, as the norm of the partition goes to 0, so you take it and chop it up into tiny, tiny subarcs, this is going to give you an integral fxy ds. And you're going to see the letter C here. That means, and that tells you that this integral is a line integral. That's how you know the difference between a regular single integral and a line integral single integral. You're going to see a C down there. Okay, the 3D version, we just did the Riemann sum for that. Looks similar. You're going to take the limit as your norm of your partition goes to 0, and you're going to have your density function be a function of 3 variables, x, y, and z. That's why I have f(x) sub I, y sub I, z sub I. Little subarc of your I subarc, and this is going to turn into whoosh, a line integral, except your density function is a function of 3 variables. Okay, now nowhere in this definition does it tell you how to evaluate a line integral. It's just a definition, so it's kind of useless. Well, how do you evaluate a line integral? What you're going to have to do is you're going to have to turn it into a regular single integral, the kind that, you know, Calc 1 and Calc 2 people could do. But you have to be very careful because it ain't that easy sometimes. What do you mean? Well, this delta s sub I, which turns into ds, that's known as the arc length element. Okay? And the arc length, hopefully I remind you of this because we did this 2 months ago. The arc length, little ds, is speed, the magnitude of velocity, dt. So if you have a 2-dimensional curve, then the speed is going to be the square root of the sum of the squares of the velocity vector, and then you got your dt. And then a similar formula holds for a space curve. You just add the z prime squared. Okay, so here's the theorem that tells you how to turn a line integral into a doable integral. So this is a key theorem. Put stars around it. It's going to be your key guy. So if you have a curve in 2D and you have x of t, y of t, and time goes from a seconds to b seconds, your regular line integral, which looks like this, you're going to turn it into a regular single integral that you can do business with. Everywhere you see x's and y's, you have to replace them because we're going to turn this into an integral where the only variable that I want to see in the whole thing is a t, time. So what are you going to replace the x's and y's with? You're going to steal the x of t and y of t off of the vector valued curve that you're integrating over, because line integrals you're integrating over a curve. So you just substitute. And then this arc length element, you're going to have to replace him with a big old nasty integral, because that's the arc length element. And I already taught you arc length back in the day, and we found arc length in vector valued functions, and there it is. It's coming back to haunt you. You thought we'd never see it again? You thought wrong. Guess what? It's back. And then the 3D version is, so if you've got a curve in 3D and somebody says, hey, go do this line integral, this 3D curve, you're going to turn it into a regular integral. You replace the x's, y's, and z's in your density function with the x of t, the y of t, and the z of t right off of the curve. And then the arc length element, oh, it's going to be this huge radical. Oh my goodness, you're going to do the magnitude of the velocity vector. You know, it's going to be this nasty big radical right here with the sum of the squares of the derivatives of the vector value curve. Okay, so there's the two line integrals. One's a 2-dimensional, the other's a 3-dimensional. And the key is you do a lot of substitutions and you get that big old arc length element, and then you hope it's even going to be integrable. Like, that's the nasty part. Like, is this even going to be integrable? Oh my God, I don't know. Let's do one problem and then I'll kick you out of here, okay? An easy problem where it's already parameterized for us. Nice. Okay, so what of it? Well, take a look at letter A here. They give you the density function x plus 2, okay? And they tell you, go do a line integral. How do you know they're asking us to do a line integral? Because they have an integral symbol with the letter C right beneath it. That means go do a line integral, okay? And they're giving you the curve, which is awfully nice of them, because sometimes you have to parameterize it yourself. So this is real special because we don't have to do as much work, but we still have to do work. So first order of business, you need to go get R prime, because you're going to use that to help you get your arc length element. And this is pretty easy to take the derivative of, let's see, the derivative of t is just 1. And then 4/3 t to the 3/2. 4/3 times 3/2, I believe, reduces to what? 2?
8
and then t to the
to,
half.
or 8t to the half.
So you're going to have 4/3
Wait,
times
no, my bad.
3/2. We're taking derivatives, not integrals. Be careful. And then the derivative of that guy, okay, I'm going to just clean this up and reduce a little bit. Okay, I think that's right. Now, what is your magnitude of velocity? What is your speed, essentially? So if you take the square root of the sum of the squares of the velocity vector like that, it turns out, after doing all the squares correctly, like that, you get that. Now what? This line integral, and I'm going pretty quickly here, but this is easy, okay? It's just substituting. They told you that time is going from 0 to 2. That was very kind of them. You don't have to come up with a range for time. And then the x plus 2, well, you don't want x, because I got to have an integral that only has a t in there, because we're going to do dt here. So what do you replace that x with?
T.
You look at the x component from your vector valued curve, and you would replace it with just t. Oh, that's nice. So you have, instead of x plus 2, t plus 2. And then this arc length element, which is pretty disgusting because you know it's that whole radical, we just did it, the square root of 1 plus 4t plus t squared. And then integrate this with respect to t. Is that even integrable? It turns out it is, using the power rule with u sub. It isn't always. Sometimes you have to get your calculator involved. So if you let u be what's underneath the radical, t squared plus 4t plus 1, du is 2t plus 4 dt. But if you factor out a 2 from 2t plus 4, the good news is the t plus 2 is already in the integral. That's good news. The only thing I need is a 2. So I can put 1 in, provided I divide 1 out. Now it looks like 1/2 square root of u du. And you know the drill. This is going to be 1/2 2/3 u to the 3/2. And then that's going to be 1/3. And if I put my u back in, which is t squared plus 4t plus 1, that whole thing to the 3/2 and evaluate between 0 and 2. And it's not going to be a very pretty answer because you're going to get like 1/3. Oh my God, you'll get like 2 squared plus 4 times 2 plus 1. That whole thing to the 3/2 minus, and then when you plug in the 0, that's just 1 to the 3/2. So that's just 1. But this right here is like 13. So I'm just going to leave it as 1/3 times the quantity 13 to the 3/2 minus 1. That's good enough for government work, okay? And at approximately 15.29, and that would be the mass of the wire if this curve were representing some wire, and with the density function, and that would be the mass. Okay, so that's a good application. I'm done. See you later. You're free to go. I'll stay a couple more minutes here if you need a quick answer.